So hi everyone, I'm Brian. I'm a software engineer at Facebook. I'm presenting work I did with my colleague Ergin and a former summer intern, Hao Yuzhang, from Princeton University. So the solution is called SOS. It's a solution for optimizing shuffle I/O in Spark. Before we dive into the solution, I want to talk a little bit about shuffle I/O in Spark, especially at large scale. So many of you have probably seen this diagram before. It shows how operations in Spark are divided into stages. And between stage 1 and stage 2, we have a shuffle operation. So what the shuffle operation does is it pushes data from one stage to another. And while it's doing this, it partitions the data so that particular partitions make it to the reducers that they have to make it to. And so shuffle is basically an all-to-all communication between these stages. And in Spark, it's actually implemented as files on disk. So the reason why shuffle is done on disk is kind of twofold. The first is that it allows strong fault tolerance guarantees. Because you're materializing your data on disk, even if some components fail, many times you're able to read your shuffle data. Another thing is that not all data on Spark jobs can actually fit into memory. So in Facebook, we see many times data that is actually 10 times larger than the available memory, even in the entire cluster. So these, obviously, you can't just keep in memory. Now, one problem that arises because we're doing shuffle I/O on disk is that the I/O actually grows quadratically with data. And I'd like to illustrate exactly what I mean by this. So first, what I have on here is a small job. Let's say it has 2 map tasks and 2 reduce tasks. And then the shuffle I/O that you see is each reducer has to read from each mapper, so you have 2 times 2 shuffle requests. Now, if you add more data and then you partition this data accordingly into more tasks, then you actually see how the data is growing quadratically. So here we have 4 map tasks, 4 reduce tasks, and now we have 4 times 4 equals 16 different shuffle requests. So like I've been talking about, the math is pretty simple. It's just M times R, number of mappers times number of reducers. Shuffle fetches are required. So what does that have in terms of practical impact? Here we have an experiment where we're adjusting the size of the data, and we're also growing the number of tasks accordingly. And we see that the I/O requests, the total I/O requests that we make, grow quadratically, as we saw in the illustration. And we also see in the green line that the shuffle time increases accordingly. Another way to look at this is that although the data inside each task remains the same, when we're actually doing the shuffle, we're actually reading smaller and smaller pieces of shuffle data from each shuffle fetch. So as you see, as we're growing the data, the actual sizes of fetches that we're doing are growing smaller. This amounts to a large amount of fragmented I/O requests, and this is just a very adversarial workload for spinning hard drives. So just to expand on that a little bit, if you're reading or writing very small pieces of data, then you have to spend a lot of time doing seeks, and then it's hard to get the full bandwidth of your hard drives. So we could think of one way to solve this would be just naively to tune the number of tasks in a job. And in some ways this makes sense. So instead of using four different map tasks, 4 different reduce tasks for this large data, maybe you could just process more data in each task. then you don't have this quadratic equation. However, this ignores one part of a Spark job, which is actually that tasks have to spill their intermediate data to disk once they exceed their memory capacity. So assuming that by increasing the amount of data that you're processing in each task, you actually induce more spills, then although we reduce the shuffle, the spills, which I indicate here with these two disk animations, you're actually increasing the amount of spills that you have to do. And that's across all of the tasks. So to summarize, executing with larger tasks, it reduces the shuffle I/O, but then it ends up increasing the spill I/O. Again, we can look at this in an experiment. So here we actually keep the size of the data in the entire job the same, but we split it across a different number of tasks. And we plot the time it takes to do the shuffle. So here, as we expected, we again see this kind of quadratic relationship where as we split the job into more and more tasks, we have to do more shuffle I/O, and it takes more time. For spills, it's actually, it grows in the opposite direction. So the more you make the tasks larger, so the number of tasks smaller, you end up doing more spill I/O. And that adds to time in your job. So here you could say the sweet spot for this job would be at around 1,000 map tasks. But it's not very practical to do this kind of tuning for every single job that we're running in Facebook. And it's also very difficult because the data volume that you do, even for periodic jobs, could change. And then the sweet spot would change. So again, to kind of recap, small tasks run into this quadratic I/O problem that we see going from left to right. But then if you instead use bulky tasks, you're actually paying the cost of spills. And not just spills, but actually, if you think of how you're supposed to write Spark jobs, you're actually discouraged from writing bulky tasks. And the reason is because this can cause, you essentially split things into larger pieces, and then it's easier to have imbalanced workload, things like stragglers, and also different overheads, such as like garbage collection and what we showed here, spills. So what we actually want is we want the benefits of small tasks, because that's how we're taught to kind of split up Spark jobs. But then this leads, when you have large shuffles, this leads to large amounts of fragmented shuffle I/O, which we don't want. What we actually want is like fewer sequential shuffle I/Os. But then this leads us to, again, bulky tasks, which is, again, what we don't want. So because of this dilemma, what we came up with is a solution called SOS. And this work has actually been presented under the name of Riffle at Eurosys 2018. So if you want more details than I have in the slides, you can actually look at the paper itself. But in addition to what we had in the paper, which were experimental results, in this talk, I also give more detail on how we deployed this at Facebook and the actual results we get from the production deployment. So what is SOS? Here I try to explain using this diagram where we have 6 mappers and then 7 reducers, and we're doing a shuffle. So each mapper produces a map output, which is what is being read by the reducer. And you can notice that I kind of color-coded this map output. What it means is that the map outputs are actually partitioned so that each reducer only has to read its small segment of the map output. And this is what's done for shuffle in Spark. So given that we weren't using SOS, what would happen is each reducer would have to read a small segment of each of these files. And that's where we get this M by R math. Instead, with SOS, what we do is we add an additional step where we take a number of these map outputs, and then we merge them into a larger shuffle file. So you can see that this combines these smaller shuffle files into larger ones, and we still keep the partitioned file layout. So we merge in a way that we keep this layout. So on the reducer side, you're essentially doing the same operation you did before, just on a smaller number of files. So now if you see, each reducer only has to fetch from, in this example, 2 files, and it's fetching a larger block within these files. So if we go back to our math that we did, the n by r, we still have n by r, but we're dividing this by what we call the merge factor. So here in this example, the merge factor would be 3. We're grouping this merge factor number of outputs together. So here I show how we actually implement this in Spark. So here I show a diagram of how Spark is running normally. So you see on the left, there's a driver. So there's a driver for each job. And the driver actually does the scheduling of each task, which is run on a cluster of machines within executors. So the driver is doing this assigning, and then tasks report back their status. And then these tasks each, they do shuffle by using a file system. So what we add is a SOS shuffle service. And if those of you who are familiar with external shuffle service, this is actually piggybacking on that external shuffle service. And we're adding capability to merge. But essentially what this is we have a long-running instance of each of these in each physical node in the cluster. And what it does is it actually merges together the files, the map files, as we saw in the previous diagram. And what controls this is actually a scheduler component that each job's driver has, which, depending on the progress of the job, it sends these merge requests and then gets reported back when these are merged. So you can see how each job controls its own merges via the SOS scheduler. So given this design, we have these are results on a synthetic workload. And I say they're unoptimized. I'll come back to why I say they're unoptimized later. But the way to look at this is the data points on the far left are what Spark does without SOS. So they're labeled no merge. You can see that there's a large number of reads, and that each read block size is pretty small. Then we have 5, 10, and 20, and 40 n-way merge. So this is the merge factor. And you can see how the read block size increases as we increase the merge factor, and the number of reads decreases. So you can see SOS reduces the number of fetch requests done by Spark by more than 10x. And now, so that was kind of the I/O side of the story. Now, if we look at how this affects compute, we can look at this graph. So again, the far left is without SOS. And we see that because we're reducing the shuffle I/O and how expensive that shuffle I/O is, we can see that the reduced stage, the time taken for the reduced stage is actually decreasing significantly as we increase the merge. However, one thing we see is that the map stage actually increases. And the reason why the map stage is increasing is we don't finish the map stage until all our merges are complete. So we kind of wait. We have this waiting time where we're waiting for these merges to complete, and we don't start the reduced stage. So overall, we still get in this experiment, we still see the job completes 35% faster, so it's a win. But we're a little concerned about this increase in map stage. So this leads to one of our first optimizations, which is best effort merge. So essentially what we're doing is, instead of waiting until all the merges are complete, we wait until a specific threshold, and then we just go ahead. So this uses the property that the merging doesn't actually change any of the data that we're reading. So we can mix in together merged and unmerged files and still get a consistent result. So in this case, we set 95% as the threshold. And we can see that this has a little bit of an adverse effect in the size of the read block size and the number of reads. But in terms of compute efficiency, we see a clear win. So we see that the map actually, the increase in the map is much less, while the reduced stage is still, the running time for the reduced stage is still reduced. And in total, we actually get a 53% faster job completion time compared to the 30-something% we saw before. So this is, you can think of this as something similar to dealing with stragglers, except here, instead of, because we don't have to always finish everything, we can kind of just cut off the stragglers at the end. So another consequence, so if you think of this as at a job level, this is 53% faster. Another way to think of it is that SOS allows this Spark job to finish with much less cluster resources, so you're becoming more efficient in your cluster. So there are a few more additional details in the implementation. For instance, the way we allow fault tolerance for merge operations is similar to the best effort merge. We just handle it by falling back to unmerged files. So if you fail to do a merge operation, you can just proceed using the previously unmerged files. We also did some work making sure that we're doing efficient memory management in the merger component. As the diagram suggests, we use large buffers to read, and then we also use large buffers to write this. And we do this to have high throughput and also not to have too many disk IOs while we're doing the merge itself. So now I'd like to discuss about our deployment and the gains that we observed with the deployment. So we started deploying this late last year in a staged rollout, and then we completed this rollout in April. So we've been running essentially all of Spark for over a month. We've been running stably using SOS. And one thing that was interesting when we did the deployment, we decided actually to do the deployment using SOS and actually combining this with Z-standard compression. And the reason we do this is, so Z-standard compression had, at least the compression ratio that we used, had more compression than our previous LZ4, but it took a little bit more CPU time. But the SOS and Z-standard kind of complement each other, and we get a net gain. So I'll just talk a little bit more about that. So if you think about I/O, there's two big things, spill I/O and shuffle I/O. In the case of spill I/O, we say SOS actually has a regression. If you recall, we do this extra merging step, which requires you to read the spill and then write it again in its merged format. But in terms of Z-standard, we actually get a gain because Z-standard has better compression. And for these spills, we actually get a pretty good compression ratio. So in net, we get a small gain here. With shuffle I/O, which is the main focus of SOS, we get a significant gain. And then Z-standard, because it compresses it compresses everything a little bit better, we get a smaller gain, and then we get in net a big gain. And let's also talk about this a bit in terms of compute efficiency. So we use a few metrics in compute efficiency, but what we really care about is what we call reserved CPU time. It's the amount of time that we spend allocated CPU. And then what I have here in CPU time is actually what the actual CPU you're using. So this is more of a pure CPU metric. So in terms of Z-standard, we see a small regression in CPU time because, again, the compression is more, It takes more time than LZ4 to do the compression, even though it does a better job of compressing. But what we really care about, again, is this reserve CPU time. And we see a gain because of SOS, because our I/O is more efficient. And then Z-standard doesn't have an effect in terms of purely the I/O time. And in net, we get a gain on the reserve CPU time. So this is kind of the theoretical background behind why we do SOS and Z-standard. And now I'll show you the actual results based on our deployment. So this slide shows I/O gains just on an application request level. So this is kind of straightforward. We're making 7.5 times less requests from the Spark level. Now, what we really care about, though, is how this translates into the disk level gains. So here we use the metric called disk service time. So this is using sampled output. It's an approximation of how much time we actually spend on each of the disks in the storage system. So if you look on the left, we show the before. And here we see what we've been talking about this whole time, which is that read I/O actually takes a very long time. And this is dominated by the shuffle reads. After we deploy, we see that the disk service time actually is 2x more efficient, which is a huge win for us. And you can see the breakdown. You can see that because we're essentially targeting the shuffle workload, our read has decreased by a lot. And then we also see that the write also decreased, and this is because of the Z-standard compression. The other parts here are the labeled write merger and read merger. These are the extra overheads of having to do the merge process in SOS. And you can see that they're definitely there, but they're not a very significant part of the disk service time. Again, this is just another way to look at it. So another way to look at it is that we increase the average I/O size that the disks are doing by 2.5x. So previously, because the shuffle has this quadratic equation, we were only reading at around 500 kilobytes per I/O, but now we're up to a more healthy 1.4 megabytes. And then we can see how these I/O gains translate into compute gains here. So in total, we see a 10% gain in reserve CPU time. And the breakdown shows why this is. And as we suspected, because of the Z-standard compression, we actually see a 5% regression in pure CPU time. But that regression is more than taken care of by the efficiency gain that we get in I/O time, where we see a 75% gain, which matches a total to 10%. So again, we've deployed this for over a month. Things run stably. We're still kind of currently working on increasing the gains that we see in production. But in summary, so we talked about how large-scale shuffle looks like in Spark and how it induces large fragmented shuffle I/Os. And as a solution to this, we provide SOS, which we deployed and run stably at Facebook scale. And the gains that we've observed from this technique are 2x more efficient I/O and 10% more efficient compute. And finally, we hope to contribute this back to open source. So for those of you who are interested, please stay tuned. Thank you.
Excellent. All right. We have some time for questions.
Hi, thank you.
Hi.
So a quick question. So when you do the merging for the fragmented map side files, do you do merge on the same machine as the mapper task, or you transfer the small file to another machine and do merging there?
So so there's kind of two answers to this. So actually I have a talk later talking about dissag. But essentially if we're running in a co-located cluster where the data is all local, then we make sure to merge the data within the same machine. However, if we're actually storing our data in a distributed file system, then we don't actually care which machine we do this in. Essentially, yeah, we can do it on any machine, and it has the same cost.
So if doing in same machine, that kind of add extra I/O on that machine, so you kind of read and write twice.
Yes, yes. So as you saw, the overhead, there is some overhead. The reason why it's not prohibitive is because we're actually reading and writing in very large chunks. So instead of having to read and write in very small chunks, instead of doing random writes, we're doing long sequential reads and writes.
Wow, this is a popular talk for questions. So if you have questions, could you please come up here and form in line? Normally I would go run around, but given the number of people who want to ask, I'd appreciate it if you came to me. You can merge here, and then I don't have to do the I/O.
Hi, thank you for your talk. Can you hear me? Okay, great. I wanted to ask, how did you determine the merge factor and the best effort merge ratio, and does it differ for each job that you are running?
Sorry, it's hard to hear from here.
How did you determine the merge factor?
How do I?
The merge factor,
Okay.
and does it differ for each job that you are running?
So the best effort merge that I was talking about is the strategy for dealing with merge stragglers. Essentially, the strategy is that we can just ignore these merge stragglers. So we don't actually have to complete the merge to be able to advance. We can just use, instead of the merged output, we just use the unmerged output for those stragglers. And so there's a little bit of performance hit, but it's not very substantial. And instead, we're able to kind of reduce the latency.
So it is determined based on the time, not
so currently our strategy is based on just the percentage of completions. So the assumption there is, say, we won't get more than 5% of stragglers. And it's worked out well in practice, but you could think of using a time-based as well if you're really, if you're really concerned about latency. So we haven't implemented but that seems a very reasonable approach as well.
Hello. I would like to know, how do you merge basically one map output, and it is totally independent to the other map output, right? So how do you merge multiple maps output into the one big chunk of block?
So sorry, it's really hard to hear, but I think you're asking how do I do the merge?
Yeah, how do you merge, right, of multiple maps output into the one file, or you can say one big chunk?
Right. So you're essentially, you have the index of how these files are partitioned. So it's simple to kind of, if you think of the first partition for each map, you just have to read up to that point, and then you just have to simply concatenate these together.
What I'm asking, basically, map generates the output, right? If I have a two maps task, for example, right? One map task will generate the output, and the second map task will generate the output, right? Then how can, your merge, I think you running one extra, basically, package, or basically one Java software on every machine, right? Right? One Java process as a basically shuffle Java process extra, right? So how do you merge of two map task output into the one?
Oh, so yeah, we use the external, so we're piggybacking on the external shuffle service. So essentially, each map task will write to disk, and these files are all readable from disk. So the merge itself is done by the external shuffle service. So it's essentially just a dumb merge. You give it a list of files, and then it will just go ahead and merge those.
So the shuffle service, which it will have the information. Okay, these two map tasks belong to the one
So
job.
the way the shuffle service knows this is that each in the driver we have this component, the SOS scheduler component, and that is actually the one that.
Okay.
Sorry. Yeah. So that's actually the brains, and then the shuffle service is just gets these requests and just does it and then reports back. But the shuffler is what actually.
There is a third mapper which has.
Sorry. Yeah.
There are a lot of questions. We will not be able to get through everybody, but if you have a further question, could you just follow up with our speaker outside? Does that work for you?
Okay.
Okay.
Hi, great work. And I was just wondering, would you mind share how much of the workloads, Facebook workloads, are currently on Hive versus on Spark? Because you mentioned Facebook scale. And my second question is, do we have similar optimization for Hive workloads as well?
I see. So I don't know if we're sharing the split of, I think we're sharing that information. But there's a substantial amount of workload in both systems. That's something I can say. And yeah, actually, so we've seen this shuffle problem in Hive as well. And the Hive team actually has their own solution for this as well. The overall goals are similar. The details are a bit different. But yeah, this is definitely like, it's not just a Spark problem. It's definitely a problem for Hive and Spark.
All right, so we have hit our time limit, but I see that there are still a lot of people who have questions. If y'all would not mind just moving out.